This is GitHub. Hundreds of millions of developers use it. Here I search for JavaScript repositories and it says that there are over 3.1 million repositories with JavaScript listed as the programming language. But if you scroll down to the pagination controls, you will see only 100 pages. And while I'm paginating through the results, if I query for the page 101, I get the 404 not found page. Now, even if I use the GitHub's API to query for repositories beyond page 100, so as you can see on the screen right now, I'm querying for repos with the keyword JavaScript. The current page is 100 and per page I'm seeing 10 records. The total count is well over 3 million, but if I let's say search for page 101, like we just did, I get the error message saying that only the first 1000 search results are available with the error code 422, which means unprocessable request. Another example is this website where I can search for stock images. Here I gave the search keyword trees and it says that there are over 9 million images available to us. And if I scroll down to the pagination controls, I can see that each page is showing 48 results, which means there are roughly 18,000 pages that should exist for the query trees. But if I explicitly, let's say, search for the page 6000, the backend search query breaks and it displays this particular error message. And this is not a bug. This is not even rate limiting. Applications with such large amount of data do this intentionally. And once you understand why, you'll understand a problem that shows up in almost every app that has millions of records and has dashboards that support pagination. Now, GitHub is not being lazy. They picked the limit 1000 on purpose because letting you go deeper would mean their search engine doing a very expensive operation over and over for every user who tries it. To see what that expensive operation is, I have prepared a table named videos with 5 million rows on a Postgres server. It's a very basic table with 3 columns, ID, title, and created at timestamp, where I have defined ID as the primary key. Now, let's say I was supposed to build a dashboard with pagination control to list all of the data in this videos table. We would use queries with offset in our backend to support pagination. And let's say if we were to jump to page 50,000 with 20 results per page, that will be an offset of nearly a million. But what most developers don't realize is that the database cannot directly jump to the millionth row, even if the table is indexed. Databases keep rows sorted using a structure called a B tree or a self-balancing search tree. Now, a B tree is excellent at one specific thing, which is walking through rows in order as per the indexed values one after another, but only for the actual value which is indexed, which in our case is the ID column. So when your query says offset 1 million, it starts walking the index from the beginning of the scan all the way up to row 1 million, and only after it has discarded that many rows does it start to actually collect the 20 rows that we requested for. Let's see this query in action. I'm using Postgres here and I'll be running explain analyze on the query to see the query plan. At the bottom here, we have the execution time, which is roughly around 700 milliseconds. But if we look at the end of the index scan row, it will show the amount of rows it had to process before it could return anything. That means the cost of this query has almost nothing to do with the 20 rows that we actually wanted to fetch, but it's driven entirely by how deep the offset is. So if you're paginating to page 10, the cost is not that high. But in our example, for page 50,000, the query had to discard nearly a million rows just to reach to the part that we actually needed. Now let's talk about the solution to this problem and why most apps now don't support the traditional pagination control. Let me run a different query on the same table with the same result size of 20 records. Only difference here is that instead of asking for page 50,000 by giving an offset, I'm asking for the 20 rows after a particular ID, which in this query is 99900. And remember, ID is the column which we have indexed. Now watch the execution time. Not only the query was 300 times faster, but the most important part here is under index scan, you can see that it only had to go through the actual 20 rows that we requested. The only thing that changed in this query is how we asked the question. And this type of queries have a name: keyset pagination. They are sometimes even called cursor pagination. So instead of counting from the start, the database walks down the B tree directly to the row with the value which you asked for and read 20 rows forward from there. That's why apps like Instagram, Twitter, or Reddit don't have pagination controls or page numbers saying that currently showing post for page 4000 or something similar. They have load more or show older post actions, just like the one we have in our second query. So their queries usually look like give me what comes after this ID and not give me position 4000. So what we described is the actual trade-off developers rarely think about while deciding what their UI actually needs. Offset gives you true random access, using which we can jump to any page anytime, but our servers pay for every row that they have to skip to get to that particular page. Cursors are fast at any depth, but they only let you move forward or backward from where you are, and they do not teleport to an arbitrary page. So coming back to the example of GitHub, they only allow 1,000 search results because when we scale an application like GitHub across millions of users, and if even a small percent of those users are making such expensive queries, it will be very difficult for their servers to perform such expensive operations. So that's why websites like these just limit the number of pages which a user can access. I'm actively making videos like these on system design, and if you're interested, please subscribe to the channel and stay tuned for more such videos.